Ok. Muy bien, vamos a esperar unos minutos más para que se conecte Moisés. Y ya podemos empezar. Bueno, a lo mejor se quedó dormido porque siempre es puntual. Vamos a ver. Okay, so let's start. So what we covered last time were vector bundles. And so today we will continue discussing a little bit about, no, sorry, last time we discussed the tangent bundle. Yes. Right. So last time we discussed the tangent bundle. The tangent bundle is a manifold that we constructed by joining all of the tangent spaces at every single point of a manifold. A tangent bundle, it is a special object in a more general context, which is called vector bundles. So what we're going to do today, we will see the definition of a vector bundle, and then this will also include tangent bundles. We will see a few examples, and also remember from last time that for the tangent bundle, we also discussed what is a section of the tangent bundle. Vector bundles, they also have sections, and that's something that we will study today. And you will see that not in this language, but in a different context, in multivariable calculus, you have seen this type of vector bundles and sections. Okay, so remember from last time that I have a smooth manifold M, and then we constructed a new manifold. We denote it like this. We prove that it is a smooth manifold by giving it a very particular type of shards. Remember that the shards that we used to define the smooth structure here were given by an atlas here. I took a shard on M, and somehow we provided a shard on the tangent bundle. And also keep in mind that it has dimension 2n. Usually we will think of this tangent bundle or any bundle with a diagram like this. This is the projection map. And the preimage of every single point was the tangent space at that point. So usually we just simplify things. In that vector space, we put it Rn. So you should think that on Tm, I'm moving this way in the horizontal direction. Let's say we're moving along M, and when I move in the vertical direction, I'm moving on the tangent space. So we have two n directions. And this is what I was talking before, that the way that we have a smooth structure here, the way that we define a short was by considering first a short here. So the shards in Tm are of this type. Is basically a shard in M cross Rn. So those are the shards. And this intersection here between U and V means that this is glued to this part. And now, so gluing shards like this, we create the tangent bundle. So this tangent bundle, we have the sections, which are just smooth functions like this, but they must satisfy this condition. And this means that at every point in the domain that is on M, we assign a vector that belongs to the tangent space at that point. And so these are called sections, and this is something that you have seen on Euclidean space that corresponds to vector fields. Yeah, so this is something that you learn in calculus. Let's take Rn to be our manifold. The tangent bundle in this case is Rn times Rn. The projection is just to the first entry. So here, the first entry is a point in Rn. And, oh, right, sorry. I have a 1 here, so this is not what I wanted to say. Let me pause here. Okay, so later we will cover this. So up to this point, this is what we have seen for a manifold, the tangent bundle, right? This is the tangent bundle. With this projection map. And the idea is that above each point, the pre-image is the tangent space at that point. In particular, the pre-image has the structure of a vector space. So I have here P. The pre-image is something that we have studied before, the tangent plane, but now I would like to focus only that the pre-image has the structure of a vector bundle. So the whole idea, so now I'm moving into this. This is a 1, it's not n. I want to stress that this is n, a 1. So this, there's nothing new whatsoever, but it is the motivation for what it is coming. So take a manifold Rn, and you can construct another space, Rn times R1. The whole idea, I just want this not to be n, so that it will be something different than the tangent bundle. The idea is that this is my manifold and this is a vector space. That's how I would like to distinguish this. That's why I would put a point here, and here I wrote it like a V, that it means a vector. And you have the usual projection. You project to P. Now this picture, if I look at a point on Rn, so first, just in notation, you know that this is something like this. But what I want you to keep in mind is that the preimage of this point is a vector space. So I would like to think this has a vector space and a vector space. I just put one dimension, it could be any dimension whatsoever. And this is what we will have for a vector bundle. A vector bundle is basically this concept. I will have a big space, I have my manifold, the preimage is going to be a vector space, a real dimension, a real vector space. So this is what we will call vector bundles. Let's see the definition, and then you will see that this is something that you have seen before. So this is a different approach than when we covered the tangent bundle. The tangent bundle, we constructed the tangent bundle. Here, I'm assuming that E is a smooth manifold, and I have a smooth function pi that projects to M. So I have this. This is given now. And I'm going to say what it means for this map to be locally trivial of rank K. Okay, I have a smooth map between two manifolds, E and M, and that will be one object. And now I'm going to define what it means to be locally trivial of rank K. K is supposed to be a natural number. Okay. It's a natural number greater or equal than 1. So what it means for this to be locally trivial of rank K? Well, the first thing you might guess, locally trivial means at every point something is happening. And let's see what that is. So I want that at every point the preimage is a vector space of dimension R. That's all. There are two conditions. This is the first one. At every single point, the preimage is a vector space of dimension K. So in particular, this means that this map is surjective because the preimage is non-empty. It is a vector space of dimension K. An example of that is the tangent bundle. That's an example. This here is also an example. The preimage is a vector space of dimension 1. So this picture is very important to keep in mind. So that's the first condition. The second one is more stronger than the first one. So for every point, I would like to have a neighborhood. A neighborhood about that point. You see, up to this point, I haven't involved E or the function pi, but here it is. Such that this space is diffeomorphic to this. So this K is the one that appears here. So this is diffeomorphic to this, and with some constraint, it's not general. But the constraint is, so I want that this is a diffeomorphism, but I want a fiber, a preimage of a point, to map to RK. That's exactly what I want. So that means that this function restricted to the preimage is a linear map. Right? Remember, from point 1, that this is a vector space over the reals of dimension K. And I'm requiring this map to be a linear isomorphism, basically, between this vector space of dimension K with the standard RK vector space. Wait. Let me put it here first. The first condition is I have a smooth manifold E with a function defined on it to a manifold M. And I require that for any point that I take here, the preimage is a vector space of dimension K. That's the first condition. The second condition is, well, for every point, you have a neighborhood, U. And you have to look at the preimage of U. Okay? I want this open set on E to be diffeomorphic to something which is more or less standard, that is U times RK. This is the diffeomorphism phi. But well, I mean, there is an additional, some additional condition. Put here U and put here RK. You have this Cartesian product here. Those two sets must be diffeomorphic, but so far we only have calculus there. A diffeomorphism, a bijective map, which is differentiable, but then we put linear algebra into the condition. So above every point here, this RK needs to be under phi a linear isomorphism with the corresponding point here. And that's at every single point. This map has to be a linear isomorphism. A set U like this, it is called a trivializing open set. Trivializing open set for E. So this is what it means to be locally trivial of rank K. At every point, the image is a vector space of dimension K, and at every point on M, there's a neighborhood such that this holds. So a vector bundle of rank K is something that satisfies the above condition. You can find a cover of U's that satisfy point 2. On M, you need to find a cover of open sets, each of which is trivializing E. So this is what a vector bundle of rank K is. So this is the definition, and I'm going to give you many examples so that you are familiarized with this concept. Before that, I just want to recall some notation. M is called the base, and E the total space. Okay. So before trying to make more sense of this by having explicit examples, are there any questions? Okay, so let's see examples of this. So the first example of a vector bundle is the tangent bundle. So for any point, I even asked this question last time in class, and Jesus, you responded to this. The preimage of a point is this. So in fact, this set is a vector space of dimension n. So this complies with the first point in the definition. And now the way that we constructed TU, remember, we form an atlas like this. Remember? And we wrote something like this. Hold on. Yeah. This goes to some open set in Rn. This is a chart of M. And we constructed this. That's the chart that we gave to the tangent bundle. Okay. Or I don't remember if I wrote it like this, or maybe I wrote it like this. Phi alpha u times Rn. But again, phi of u is a diffeomorphism onto his image, so phi alpha of u is u. And even to be more explicitly, let's recall some example that we covered last time in this direction. The tangent bundle of the Euclidean space Rn is Rn times Rn. We saw the tangent bundle of the circle, that it is the cylinder, as one cross the reals. In fact, we proved that the tangent bundle of any Lie group G is precisely G times Rn. Right. So let's see another example here. Let's take E to be this, my manifold is this. So again, I would like to think of this in terms of algebra as a vector space, and this in terms of my manifold. Thus, I have this projection, and an element here, I wrote it like V just to emphasize that I'm thinking of Rk as a vector space. And that's a vector bundle of rank K. Good. So before going to the next example, remember that a manifold is obtained by gluing open sets of Rn. You glue each open set by the transition functions, and that will give you a manifold. A vector bundle, you obtain that by gluing sets of the type U times Rk. You glue them together, and that's how you come up with E or TM. And that's exactly what we're going to do in the next example. Again, this is an example that we saw last time. So let's think about the Mobius strip. But the way that we're going to look at this, here I wrote an interval, but it's going to be the whole real numbers, has a vector space. So, but I just wrote this to have an idea. So, and I want to show you exactly what I said. A vector bundle is constructed out of sets of the form U cross RK. So let me start by this and tell you how are we going to construct this as a vector bundle. So for the moment, consider this. What I'm doing here is the following. I'm considering only a strip like this. So this is like the open interval between 0 and 1. And this is R. I'm doing the same here. I have the open interval 2, 3 and R1. So I have two strips. Think about two strips of paper. And we are going to glue them in such a way that we obtain a smooth manifold that it will correspond to the Mobius strip. So here I just decided to bend it a little bit. So remember that here, so you have something like this. And I'm going to show you. So this is not a very good drawing here. So let me do it again. So I'm saying that let's see. I have these two rectangles and I'm going to fold them a little bit. And I'm going to put some rule in how am I going to glue them. On the back, which is 1 and 3, I'm just going to mash it up like this. On the front, so on the back, they are just overlapping. And on the front, I don't want the cylinder. I want the Mobius strip. So I'm going to rotate one and then glue. So it goes like this. I'm just going to glue from 0 to 1/4 and 3/4 to 1. And on the second one, from 2 to 9/4 and from 11/4 to 3. I'm going to glue green with green and purple with purple. So the green part is going to be just overposed like this. There's no twist. So in here, I'm going to define an equivalence relation to glue. So this point is here, and I'm going to match it up with a point like this. So let's see. For instance, when x is 3/4, I will get 3 and 5, 8. 8/4, which is 2. So this point is going to this one. I'm thinking that this is on this part, and this point belongs to this one. That's my relation. And now the vector, whatever you have here, I'm just going to match it up like that. I don't change anything. So again, just what I'm doing is matching up like this. So I have them, glue them together. So this is the back that I just described. Now I would like to focus here, which is the green part and the green part. I'm going to do exactly the same, except that I have minus b. So that's exactly, I'm not doing this, I'm switching and then gluing in order to have this. So again, you can, this is here, this one belongs here, and I have a relation in order to glue those points. So I mean, x cannot be 0, but assume that x is 0, then it will go to 3. So points here go here. If x is 1/4, then 12/4 minus 1/4, 11/4. So this part is just telling you what are you going to map. And the second one, you have to twist and then glue. So this space under these identifications is the Mobius strip. That's how we define that smooth manifold. And when V is 0, we can think of that as the circle. And that's our projection map. So this is an example of a vector bundle over the circle of rank 1. The preimage of any point here is going to be a real line. Right? So this circle, think when V is 0, 0 and 0. So you are joining two intervals to create the circle. Also, what I have here, this is the way that we are having E to be locally trivial. The preimage of a set is diffeomorphic to this, and this is the other one. So this is an example of a smooth vector bundle over the circle of rank 1. So just to recall what we have seen, on S1 so far we have two vector bundles. That we have seen so far. The one of this example, oops, sorry. And the other one, which is the tangent bundle. So give me a second.
Estoy muteado, profe.
Yeah, gracias, ahora sí ya. Okay, so, right, thank you. So again, on the circle, we have seen two vector bundles. The tangent bundle and the one that we have seen today, which is this vector bundle also of rank 1, right? That's also important. They are both of rank 1. The Mobius strip and the cylinder are the two vector bundles that we have seen on the circle. Okay, so again, I try to do this like this, just to emphasize this definition that we see, that it was here. So it looks awkward or complicated, but I want you to feel comfortable that it's not that bizarre by understanding this example here. Okay, so any questions?
For the mapping pipe, we map it to circle. It's like there is a middle step where we map the line or sort of line to the circle.
Right, right. So basically, what I need to make precise, uh, how do I think about the circle in this thing? So the way that I would like to think about the circle is like this. I mean, first of all, so on E, I have equivalence classes. It is X, comma, V. And basically, this is going to be X. But then, how am I thinking about the circle here? So it is the interval 0, 1, union 2, 3, with some identification. And what am I doing to create a circle? Now I'm going to make this drawing here, okay? To come up with the circle. So let's see if this works. No, I wanted to rotate this. Okay. Let me put this like this, and this 0, 1, 2, and 3. And remember that near 1 and 2, oh no, sorry, let me put it the other way around. Now remember that these points are identified with these ones here. And these points are identified like this. So S1 is the union of these two intervals, but there's some identification. And that identification is precisely this. I'm going to bend this interval 0, 1, 3, 2. And now I'm going to, so let's wait a few moments. Jesus has just logged out, so let's wait until he gets back. So in the meantime, let me make this more precise. Okay, you're back now. Right, okay, let's continue. So, so how do I think of this? That's your question. On E, I have this relation. So I write the points like this. And basically what I'm saying is this projection maps this to X, or if you would like to be even more precise, to this class. But what is this? How do I think of this circle? So let's remember how we constructed the Mobius strip using this interval and this one. That's why I would like to think of the circle in this way. The union of two intervals, this one, and some relation among those two. And these are identified with this, and these points are identified with these ones. Here we have the explicit identification. Only the points between 3/4 and 1 and 0 and 1/4. So this is the explicit formula that goes like this. So those O intervals, I put it in a vertical shape. So this go with this one, this go with that one. So I bend them a little bit. And then I match it up. Okay? So here, this is just and this is the quotient. Okay? Now, okay, first. Salvador, this makes sense?
Yes, it does.
Okay. Now, I just want to emphasize on this. I want to identify this with this. And the way that we do it is not like this. It's exactly like this. We have to, they actually touch each other. And that's important in order to have a smooth manifold. So I have this. And the relation that I have above is precisely like this. This point agrees with this one, that one with that one, that one with that one. And that's how we drew. So they agree on an open set, and that's very important. So here, phi, let's say of 1/4, 1/8, comma v is goes to 1/8. But it is the same as 11/8. Oh no, sorry. I put 1/8. perdón, puse la fórmula de acá, pero el 1/8 está aquí, pero usé esta fórmula. Estoy mal. Tengo que usar esta de aquí. Esto está mal. Perdón. Yeah, so 1/8 is here. So it should be the same as 1/8. Oh no, sorry. So now it's right. Okay, so that's how this map is defined. Okay. So this is a vector bundle over the circle of rank 1. Any other questions?
No, thank you.
Okay. Great. So well, I just wanted to well, this is not. I already covered this, so let me erase this observation. Okay, so this is examples of vector bundles. And I insist, keep in mind either the Mobius strip or the cylinder. That will give you a great division into vector bundles or tangent bundles. So now let's see what are the sections here. Let's see something that it is related to a vector bundle. So we have a vector bundle, and a section is going to be a smooth function that goes in the other way, such that it satisfies this condition. Is exactly the same that we saw last time for a vector field. At every point, we assign a vector on the tangent space of that point. Here, there's no tangent space. The only requirement is at every point, we assign a vector in that over that point. This is what is equivalent. S of p has to be a vector, sorry, in this vector space. That's what a section is, a smooth function with that. And at the end of the class, in the last half hour or so, we will see more examples of vector bundles that you have seen before, but not in that language. And also you have seen sections, but that will come later on. So the notation for the space of smooth sections is either this one or that one. And again, when the vector bundle is the tangent bundle, the space of sections is usually denoted this way. what we saw last time. That's the notation. Okay, let's see example of sections of vector bundles. And I will start first give you examples of section in tangent bundles, very particular vector bundles. So I'm going to consider Tn. So let's start on the things that you know very well. And this is what you have seen in multivariable calculus. This is a vector field. Sometimes we will omit this and just write it like this. It should be understood that it's at this point. So I'm using the coordinates x, y on R2. And you have even drawn this vector field. So this is a section of the tangent bundle of R2. Again, you know very well that this is only this. Has a manifold. R2 times R2. Okay, so now I just draw this vector field here. It is a constant vector field along R2. Again, same manifold, but a different section. So note that I'm not saying where this goes, but it should be implicit. And also this one on x comma y. So we have another section of the tangent bundle that is a vector field on R2. And it looks like this. Right, so remember that here is x comma y. And then I'm drawing the tangent vector. So that's the picture of a section on the same tangent bundle, T of R2. Okay? So let's say that this is 1, 2, 3, like this. Then this is precisely y 3 at the point 0, 3. Okay? Only that arrow. You can do it for the other ones. So before giving more examples, I would really like to emphasize this. The tangent bundle is in particular a vector bundle over the same manifold. I mean, they are the same type of objects, vector bundles, but in some situation, Tm is very particular than the other ones. And that's what I would like to stress here, especially for the things that we have learned so far. So here, B1 and B2 are not only vectors in that space, they are derivations. Right? And by one of the homework problems, when you think of those vectors as derivations, you know this. That this is also a derivation. Right? Unlike here, okay, I mean, that's true, you can have a vector and that's it, it's only a vector so far. There's nothing that you can do beyond that. Because there's not the structure of a derivation, it's just some vector space over the point Q. So in that way, on the space of section of this, you have more structure than on this one. Okay, so sometimes this is very, very useful in that sense. There are some vector bundles where you can also do a lot of things, but in general, it's just only a vector, and that's it. Okay, so I just wanted to make clear that TM is special among all of the vector bundles in that way. So I want to see more examples of vector bundles. And with this list of vector bundles, exactly what I would like to stress, we are going to see vector bundles that you have already seen before, but not in this context. So our manifold will be Euclidean space, Rn. And also it could be any open set in Rn if you want. Now, so this is a vector space. Something that that we use this very much is because there's a canonical identification with Rn, right? Because here, remember, you take this, you are using the standard coordinates on Euclidean space. And that's how you identify this with Rn. There's a canonical identification between the tangent space at a point in Rn and the vector space Rn. So I have this. I would like to think of this just as a vector space, Rn. So this is the tangent bundle of Rn, right? So I like to think of this Rn. Let's say, let me write it like this instead. The vector space is Rn, isomorphic to this one. Okay then. I have a vector bundle that corresponds to the tangent bundle of Rn. Now, something that happens in this context of vector bundles is that you use all of your knowledge of linear algebra, and everything that you know of linear algebra applies here. In other words, if you are doing linear algebra, you should now think of linear algebra like this: a vector space over a point. And now what we are doing, so to speak, is like a parametric version of linear algebra. Now what we are doing here is we have M, and above every point of M, you have some vector space. That's what a vector bundle is. So this is the concept of vector bundle. At every point, you have a vector space. In linear algebra, there was only one point. So you never look at this, you just have a vector space, and you did linear algebra. So now let's do linear algebra in this context. So V is Rn. Rn times V is the tangent bundle of Rn. And I would like to keep V here. Knowing linear algebra, I can talk about this. Let me write it correctly here. This is, oops. Rn dual and canonically isomorphic to M. Sorry, Rn. So I look at the dual space of the linear algebra. I have a vector space, look at the dual. And what I have now is a new vector bundle. So I agree, a vector space is isomorphic to its dual. But it really makes sense to distinguish and not make them the same. They are very different. So I have this new vector bundle, and the way to think about it, above every point, I have a dual vector space that is dual to the tangent space. And in this language, what is a section? Well, first, the definition is a function, a smooth function from here to here. And at every point, I assign a vector above that point. In this case, because I'm using the dual space, I'm writing that vector as V star, sometimes called a covector. Okay, now Jesus has left the class. Let's wait a few minutes. In the meantime, any questions? I said, a ver, ya llegaste, Jesús, un minutito y continuamos. Okay, so now we're back in business. Yes.
Yes.
Okay. Again, so the thing is, I have a new vector bundle, Rn times Rn dual. And what is a section here? So again, it's a good function like this. This is a vector, we know that, but it is a vector that lies in the dual vector space. Or if you want here. And now this is what we have seen and you saw in calculus. In coordinates, this is spanned by these vectors, right? And I'm going to define something that you have already seen. In this vector space, we define on the dual another set of vectors which is dual to this basis. Which means this. So this is a covector. It's on the dual, so I can evaluate it at these vectors. And that's the relation of the dual basis. Right? So the dual is generated by this. N vectors or N covectors if you want. So we can write a section like this now. So that's a section, that's a general expression for a section of this tangent, of this vector bundle. And you have seen this before. So this is a differential one form. On Rn. So the differential forms on Rn or on open subsets of Rn that you studied before correspond to sections. So, any questions so far?
No.
Okay. Now, I'm going to follow the same idea of thoughts. I have the same vector space, but again, linear algebra. Instead of taking the dual, and well, we said that this is canonical isomorphic. Instead of taking the dual, I'm going to take the exterior algebra, K exterior algebra of V star. Do you remember what is this? How is this defined?
I remember reading about it.
No or yes?
No.
No. So let's see. So you have to look at maps. Yes. So I took V star. So this is a map. It has to be K-linear. And this is, so at this point you take all possible K-linear maps. So we have, again, it is just linear algebra because I'm not looking at any kind of math. They have to be linear on each entry, and we have k of them. And the requirement is that if I make a permutation of this, f has to be antisymmetric. So f v1 up to vk has to be equal to the sign of the permutation. And that's going to be either +1 or -1. And then this is going to be sigma 1. So the set of all k linear maps that satisfy this happens to be a finite dimensional vector space, real vector space. And that's the k exterior algebra of V star. Okay? So this set is a vector space which is denoted like this. Now, again, using this fact and this, right, I mean, right, for instance, when k equals 1, there is nothing here because this is only the identity permutation when k equals 1. Like this. Yeah, and that reminds me, maybe I don't need this. Only like that. Right? For this, you look at linear maps from B to R. This is nothing because k is 1, the permutation group is just the identity, so you don't require this. So for k equals 1, this is just the dual. And this is what we have here, right? Yeah, so I think this is just like this. So it is a vector space, and it is generated by this. Here I have the wedge product, and I have k products here. I1 up to ik. Remember that this comes from this. Okay, so this is a new vector space. This is a new vector space that we have. And so I have this vector bundle. K between 1 and n. And a section is precisely a differential K form. So in this case, a section like this. And it will be the RI1, the RIK. And we have the same requirements. So that's what a section is for this vector bundle over Rn. It's just K differential forms. Okay. So with this list of examples, I really wanted to stress that one way or another, you have encountered vector bundles and sections. And you have seen this for Euclidean space or open sets in Euclidean space. The most general is this type of vector bundle over Rn, where the sections corresponds to differential K forms. Okay, questions or comments?
No, it's fine.
Okay, very good. Now, just to finish this, I'm going to say something about the set of sections in general, not only on Rn, but it is something that you have worked before with this type of elements. So I have a vector bundle, I have this space of sections, and I can define two new sections. If I take a section and a function, I define a new section. This is a real number. This is a vector. So this is the scalar product. or the sum of two sections, which is given by the sum on each vector space above a point. I just want to stress where this operation is and also this one. Because I want you to be aware of what's going on here. So that's the advantage that the preimage of every point has the structure of a vector space. So you can add vectors or multiply by scalar. And the proposition, which I'm not going to prove, is just that these two objects happen to be sections as well. They are smooth and satisfy everything that you are required in order to be a section. And again, you have worked with the sum of differential forms in Rn, and also multiplication of differential forms by a function. So in that setting, you know this proposition and you have used it before. So just to wrap it up, in terms of more fancy terms, this is a module over the ring of smooth functions on the manifold. Okay? Great. So this is what I had planned to do today, only vector bundles, example of vector bundles, sections, example of sections, and it is something that you have seen before. Remember that the space of sections for the tangent bundle are the vector fields. So next class, we're going to study vector fields. When we cover vectors, or when we define the tangent space, I told you to look up the theorem of ODEs, existence and uniqueness, or differential equations. We will use it when we study vector fields. So maybe by tomorrow, we will use that result that we haven't used before. The existence and uniqueness of solutions for a system of differential equations. Okay, so this is all that I have planned for today. Any questions or comments?
No, I don't think so.
Right. Thus, we will study these two objects a little bit more in detail, but only for tangent bundles. We will use that, and I don't know if we will continue to see vector bundles. They are extremely important in differential geometry. So it is important that you know this, you get used to it, and you feel comfortable using this language. Great. So see you tomorrow.
All right. See you tomorrow.